In my today's lecture, I want to discuss the different types of generators used in wind machine and mills. The different types of generators are classified like that: the DC generator, then the AC generator. The AC generator are again classified by the synchronous generator and the alternator. The DC generator produces direct power while an AC generator produces the alternating power. The synchronous generator and the alternator is an electrical machine that converts the mechanical power from a prime mover into an AC electrical power at a particular voltage and frequency. The synchronous motor always runs at a constant speed called the synchronous speed. The main difference between them is in regard to what spins and what is fixed. In an alternator, the electricity is produced when a magnetic field spins inside the stator. In a generator, on the other hand, the armature or the windings of wires spin inside a fixed magnetic field to generate the electricity. The generators have to be polarized after installation. There is no need for polarization in the alternators. The alternator brushes last longer than those of the generators. An alternator will not charge a dead battery, and if you do try to charge it, there is a possibility that it will burn out. But a generator, however, can be used for charging a dead battery. The alternators can fit into a small space while the generators are larger in size. The alternators conserve the energy by using only the energy that is needed, while the generators use all the energy that is produced. The DC generator again classified by the self-excited DC generators, the separately excited DC generators, and the permanent magnet DC generators. The self-excited DC generators, here the field coils excited by the generator itself. In the separately excited DC generators, the field coils are excited by some external source, and the permanent magnet DC generators, here the field coils excited by the permanent magnets. A simple self-excited DC generator may be constructed in a variety of ways depending upon the relationship and interconnection of each of the magnetic field coils with respect to the armature. The two basic connections for a self-excited DC machine are the shunt-wound DC generator and the series-wound DC generator and the compound-wound DC generator. The shunt-wound DC generator, in which the main field windings is connected in parallel with the armature, and the series-wound DC generator has the current carrying field winding connected in series with the armature. Each type of DC generator construction has certain advantages and the disadvantages. In series-wound generators, the output voltage is directly proportional with the load current, but in shunt-wound generators, the output voltage is inversely proportional to the load current. A combination of these two types of generators can overcome the disadvantages of both. This combination of windings is called the compound-wound DC generator. Now come to the basic principles of generators used in windmills. Both of the AC and DC generators produce the electrical power based on the principles of Faraday's law of electromagnetic induction. This law states that when a conductor moves in a magnetic field, it cuts magnetic lines of force, which induces an electromagnetic force in the conductor. The magnitude of this induced EMF depends upon the rate of change of flux, that is magnetic line force, linkage with the conductor as shown in the figure. This EMF will cause a current to flow if the conductor circuit is closed. Hence, the most basic two essential parts of a generator are the magnetic field. This is the magnetic field created by the magnet. This is the north pole and this is the south pole. This is the magnetic field created by the magnets, and the conductor which move inside the magnetic field. This is the conductor which is rotating inside the magnetic field. This is the another overview of the basic principles, that is the electric current supplied externally through the commutators. The magnetic force is F is equal to I into L into B. This is the flux density. Acts the perpendicular to both wire and the magnetic field as the Faraday's law. So when the electric current passes through a coil in a magnetic field, the magnetic force produces a torque which turns the DC motor. Now the basics of DC generators used in the windmills. In the figure, a single loop of conductor of rectangular shape is placed between the two opposite poles, north pole and south poles of the magnet. Let us consider the rectangular loop of the conductor is A, B, C, D, A, B, C and D, which rotates inside the magnetic field about its axis A and B. Now, when the loop rotates from its vertical position to its horizontal position, it cuts the flux lines of the field. During this movement, two sides such that the AB and CD of the loop cut the flux lines, there will be an EMF induced in these both of the sides AB and BC of the loop. The gray color arrow denotes the direction of the flux, and the green color is the direction of the current. In this case, the current direction is from A to B and at the north pole side, that is C to D. Now as the loop gets closed, there will be a current circulating through the loop. The direction of the current can be determined by the Fleming's right-hand rule. This rule says that if you stretch thumb, index finger and the middle finger of your right hand perpendicular to each other, then the thumbs indicates the direction of motion of the conductor and the index finger indicates the direction of the magnetic field, such that the N pole to the south pole, and the middle finger indicates the direction of the flow of the current through the conductor. Now if we apply this right hand rule, we will see that at this horizontal position of the loop, the current will flow from the point A to B, and on the other side the loop current will flow from C to D. So if we allow the loop to move further, it will come again to its vertical position, but now the upper side of the loop will be CD. Upper side of the loop will be CD and the lower side will be AB. At this position, the tangential motion of the sides of the loop is parallel to the flux lines of the field. Hence, there will be no question of flux cutting, and consequently there will be no current in the loop. If the loop rotates further, it comes to again in the horizontal position as shown in the figure. But now set the AB side of the loop comes in front of the North Pole and the CD comes in front of the South Pole, such that just opposite to the previous horizontal position as shown in the figure. Here the tangential motion of the side of the loop is perpendicular to the flux lines. Hence, the rate of flux cutting is maximum here, and according to the Fleming's right hand rule, at this position the current flows from B to A, and on the another side, that is D to C. So the current flows direction is from D to C in front of the South Pole, and from B to A in front of the North Pole. Now, if the loop is continued to rotate about its axis, every time the side AB comes in front of S pole and the current flows from A to B. Again, when it comes in front of North Pole, the current flows from B to A as shown in the figure. Similarly, every time the side CD comes in front of S pole, the current flows from D to C. When the side CD comes in front of N pole, the current from C to D as shown in the figure. So we can conclude that each side of the loop comes in front of N pole, the current will flow through that side in the same direction such that the downward to the reference plane. Similarly, each side of the loop comes in front of S pole, the current through it flows in the same direction such that the upwards from the reference plane. Now the working principles of the DC generators used in the windmills. Now the loop is opened and connected it with a split ring as shown in the figure. Split rings made of a conducting cylinder gets cut into the two halves or segments insulated from each other. This is the cylindrical shape. We connect the external load terminals with two carbon brushes which rest of these split slip ring segments. We can see that in the first half of the revolution, the current always flows along the AB, L, M, C, D, like that. L, A, B, L, M, then C and D, such that the brush number 1 in contact with the segment A. This is the brush number 1 in contact with the segment A. This is the segment A. Now, in the next half revolution in the figure, the direction of the induced current in the coil is reversed. DCLMBA. But at the same time, the position of the segments A and B are also reversed. Here this is A connected with the brush 1 and here the B connected with the brush 1. So the segments A and B are also reversed, which results that the brush number 1 comes in touch with the segment B as shown in the second figure. Hence the current in the load resistance again flows from L to M. Now the waveform of the current through the load circuit is shown in the figure. This current is unidirectional. This current is unidirectional. The positions of the brushes of DC generator are so that the changeover of the segments A and B from one brush to other takes place when the plane of rotating coil is at a right angle to the plane of the lines of force. This is the brass A and brass B. It is to become in that position, the induced EMF in the coil is 0. Now the series wound DC generator used in the windmills. The field current in a series wound generator is the same as the current the generator delivers to the load as they are both in series. This is the series winding. The coil is connected in series to the DC motor. If the connected load is small and only draws a small amount of current, the excitation current is also very small. Therefore, the magnetic field of the series field winding is too weak and generates the voltage is also very low. Likewise, if the connected load draws a large current, the excitation current is also very high. Therefore, the magnetic field of the series field winding is very strong and generates the voltage is very high. This is the simple circuit of the series wound generator. This is the motor. This is the armature. This is the two brushes. This is the series field and this is the load. In this type of generators, the field windings are connected in series as shown in figure with the armature conductors as shown in the figure. Whole current flows through the field coils as well as the load. Whole current flows through the series field and the load. A series field winding carries the full load current. It is designed with relatively few turns of thick wire. The electrical resistance of series field winding is therefore very low, nearly 0.5 ohm. Now here the ISC is the current flowing through the series field. IA is the armature current and EG is the generated EMF. Then the IA is equal to ISC is equal to IL, where IL is the load current, is equal to I. Voltage across the load is equal to V is equal to EG minus I into IA into RA, where RA is the armature resistance. Then the power generated is equal to the EG into I. So the power delivered to the load is equal to PL is equal to V into I. Now the shunt wound DC generator used in the windmills, where the field windings are connected parallel to the DC motor. In these generators, the field current and hence the magnetic field increases with the operating speed as it is dependent upon the output voltage. The armature voltage and the electrical torque also increase with the speed. The shunt wound generator operating at a constant field speed under the varying load conditions has a much more stable voltage output than does the series wound generator. However, as the load current increases, the internal power loss across the armature causes the output voltage to decrease the proportionality. As a result, the current through the field decreases, reducing the magnetic field and causing the voltage to decrease even more. And if the load current is much higher than the design of the generator, the reduction in output voltage becomes so severe, resulting in large internal armature losses and overheating of the generator. As a result, the shunt-wound DC generators are not normally used for large constant electric load. Now, in this type of DC generators, the field windings are connected in parallel with the armature conductor as shown in the figure. In shunt-wound generators, the voltage in the field winding is same as the voltage across the terminal. Hence, the armature current IA is dividing into two parts. One is the shunt field ISH and another is through the load as the load current IL. So the IA is the IL plus ISH. The effective power across the load will be maximum when the IL will be maximum. So it is required to keep the shunt field current as the small as possible. For this purpose, the resistance of the shunt field winding generally kept high 100 ohm and large number of turns are used for the desired EMF. The shunt field current is equal to the ISH is equal to V by RSH. The voltage across the load is equal to the V is equal to Eg minus Ia into Ra, where Ra is the armature resistance and Ia is the armature current. The power generated is equal to the Pg is equal to Eg cross Ia, and the power delivered to the load is equal to PL is equal to V cross IL. So both the shunt wound and the series wound self-excited DC generators have the disadvantages in that changes in load current causes the severe changes in generator output voltage due to the armature reaction, and as a result these types of DC generators are seldom used as wind turbine generators. However, a compound connected DC generator has a combination of both the shunt and the series windings incorporated into a single generator, and which can be so connected as to produce either a short shunt compound DC generator or a long shunt compound DC generator. This type of self-excited DC generator design allows for the advantage of each type to included into one single DC machine. The compound wound generators have both the series field winding and the shunt field windings. One winding is placed in series with the armature and the other is placed in parallel with the armature. This type of DC generators may be of two types: short shunt compound wound generator and the long shunt compound wound generator. It is mainly two types, that is short shunt and the long shunt, which I already. Now the short shunt compound wound DC generators, that is the short shunt compound wound DC generators are generators where only the shunt field winding is in parallel with the armature winding as shown in the figure. This is the shunt field are connected with parallel to the armature, and the series field current is equal to ISC is equal to IL, and the shunt field current is equal to ISH is equal to V plus ISC RSC by RSH. RSH is the shunt field resistance. Now the short shunt compound wound DC generators used in the windmills, that is the armature current is equal to IA is equal to ISH plus IL. So the voltage across the load is equal to the V is equal to the EG minus the IARA minus the ISC RSC. So this is the B. So the power generated is equal to Pg is equal to Eg cross Ia, and the power delivered to the load is equal to the PL is equal to V cross IL. Now the long shunt wound compound wound DC generators, that is the this type of wound DC generator are generators where the shunt field winding is in the parallel with the both the series field and the armature winding. This is the series field and this is the armature winding. So the shunt field is the parallel with both of the series field and the armature field or the armature winding. The shunt field current here is equal to ISC is equal to V by RSH, and where the armature current IA is equal to the series current series field current. So the ISC is equal to the IL plus RSH. Now the voltage across the load is equal to V is equal to EG minus IARA minus ISC RSC. So this is the RSC. So ISC RSC. That means the EG minus of IARA plus ISC RSC. So that is the EG is equal to minus IA into RA plus RSC. So now the power generated is equal to PG equal to EG cross IA, and the power delivered to the load is equal to PL is equal to V cross IL. In a compound wound generator, the shunt field is stronger than the series field, and when the series field assists the shunt field generator is said to be commutatively compound wound. And on the other hand, if the series field opposes the shunt field, then the generator is said to be the differential compounding wound generator. And separately excited DC generators are the way to overcome the disadvantage of the self-excited DC generator is to allow the field windings to be externally connected. This is the externally connected winding, and this then produces the another type of DC generator called the separately excited DC generator, where the IA is the armature current, IL is the load current, V is the terminal voltage, and EG is the generated EMF or the electromagnetic force. These are the generators whose field magnets are energized by some external DC source, such as the battery as shown in the figure. The circuit diagram of separately excited DC generator is shown in the figure. Now the voltage drop in the armature is IA cross RA. Let the IA is equal to IL is equal to I. Now the voltage across the load V is equal to I cross RA, and the power generated is equal to PG is equal to IG into I, and the power delivered to the external load is equal to PL is equal to V cross I. Now the another type of DC generator is the permanent magnet type DC generator. However, the DC generators for wind turbine applications have the disadvantages that a separate direct current power source is needed to excite the shunt field. Then we can overcome this disadvantage by replacing the field winding with the permanent magnets, creating a permanent magnet DC generator or the PMDC generator. When the flux in the magnetic circuit is created through the use of permanent magnets, then it is known as the permanent magnet DC generator. It consists of an armature. This is the armature, and one or several permanent magnets situated around the armature. So these are the this is the armature, and this is the windings, and this is the rotor coils, and this is the stator magnets. Okay. Now these DC machines consist of a stator. This is the stator, and this is the stator shown in the figure. These stators having the rare earth permanent magnets such as the neodymium or the samarium cobalt to produce a very strong stator field flux instead of wound coils, and a commutator connected through the brushes to a wound armature as before. The main advantage over other types of DC generator is that the permanent magnet DC generator responds to changes in wind speed very quickly because their strong stator field is always there and constant. Permanent magnet DC generators are generally lighter than the wound stator machines for a given power rating and have the better efficiencies because there are no field windings and the field coil losses there. Also, as the stator is provided with a permanent magnet pole system, it is resistant to the effects of possible dirt ingress. However, if not fully sealed, the permanent magnets will attract the ferromagnetic dust and the metallic swirl, also called the turnings or fillings, which may cause the internal damage. So the permanent magnet DC generator is a good choice for the small scale wind turbine systems as they are reliable, can operate at low rotational speeds and provide the good efficiency, especially in light wind conditions as their cutting point is fairly low. There are many off-the-shelf permanent magnet DC generators are available with a wide range of power outputs from a few watts to the many of the 1000 watts. The DC voltage generated by a permanent magnet, the DC machine, is governed by the following three factors. Number one is the magnetic field developed by the stator. This depends upon the physical size of the generator and the strength and the type of the permanent magnet is used. The second is the number of turns or loops of wire on the armature. This value is fixed by the physical size of the generator and armature and by the size of the wire conductor. The more turns used, the higher the output voltage. The larger the wire diameter or the cross-sectional area, the higher the current. And the third point is the rotational speed of the armature, which is governed by the speed of the rotor blades relative to the wind velocity. For PMDC generators and motors, the output voltage is proportional to the speed and is generally like the DC generator in the previous tutorial. The operation of a synchronous generator is also based on the Faraday's law of electromagnetic induction, working in a similar fashion to an automatic type alternator. The difference this type is that the synchronous generator generates a three-phase AC voltage output from its stator windings, unlike the DC generator which produces a single DC or the direct current output. The single-phase synchronous generators are also available for low-power domestic wind turbine synchronous generator system. Basically, the synchronous generator is a synchronous electromechanical machine used as a generator and consists of a magnetic field on the rotor that rotates and a stationary stator containing the multiple windings that supplies the generated power. The rotor's magnetic field system is created by using either the permanent magnets mounted directly onto the rotor or energized electromagnetically by an external DC current flowing in the rotor field windings. The main components of a synchronous generator is the stator. The stator carries the three separate armature windings, physically and electrically displaced from each other by 120 degrees, producing an AC voltage output. These are the stator windings. Three stator windings, 120 degrees separation. Another is the rotor. This is the rotor. This is the rotor. The rotor carries the magnetic field either as permanent magnets or the wound field coils connected to an external DC power source. This is the external DC power source via the slip ring and the carbon brushes. The working principle of the synchronous generator used in the windmills. The field windings are the windings producing the main magnetic field, which are the rotor windings for a synchronous machine, and the armature windings are the windings where the main voltage is induced, usually called the stator winding. These are the stator winding and this is the rotor winding. In other words, for a synchronous machine, the rotor windings are the field windings and the stator windings are the armature windings. These are the armature windings and this is the field windings. This rotor winding is connected to a DC supply. The rotor winding is connected to the DC supply voltage, producing a field of current, that is IF. This is the IF, excitation current. circuit diagram of the full bridge 3-phase AC to DC rectifier is shown in the figure. In this configuration, the wind turbine can operate the generator at a frequency independent of the synchronous frequency, as changing the generator speed varies the generator frequency. Hence, it is possible to vary the speed of the generator over a wider range and to run at the optimal speed to obtain the maximum power depending on the actual wind speed. Note that the output voltage from the 3-phase bridge rectifier is not the pure DC. The output voltage has a DC level together with a large AC. The waveform is generally known as the pulsating DC. This is the pulsating DC waveform. This is the pulsating DC waveform, which can be used to charge the batteries but cannot be used as a satisfactory DC supply. In order to remove this AC ripple content, a filter or the smoothing circuit is used. These smoothing circuits or the ripple filter circuits use the combinations of inductors and capacitors to produce a smooth DC voltage and current. Now, when used as part of a grid connected system, the synchronous machines can only be connected to the mains grid when their frequency, phase angle and the output voltage are the same as the grids. In other words, they are rotating at their synchronous speed, as we have seen in the tutorial. But by rectifying their variable output voltage and frequency into a steady DC supply, we can now convert this DC voltage into an AC supply of the correct frequency and amplitude, matching that of the mains utility grid by using either a single phase or a 3-phase inverter. An inverter is a device that converts the direct current DC electricity to alternating current AC electricity which can be fed directly into the mains grid, as grid connected inverters operate in sync with the utility grid and produce the electricity that's identical to the utility grid power. Grid connected sine wave inverters for wind systems are selected with an input range that corresponds to the rectified output voltage of the turbine. Then the advantage of an indirect grid connection is that it is possible to run the wind turbine at variable speeds. Another advantage of rectifying the output from the generator is that wind turbines with synchronous generators, which use the electromagnets in their rotor design, can use this DC to supply the coil windings around the electromagnets in the rotor. Now come to the last part, that is the alternator, which is used in the windmills. An alternator is an electrical generator that converts the mechanical energy to the electrical energy in the form of alternating current. For reasons of cost and simplicity, most of the alternators use a rotating magnetic field with a stationary armature. Occasionally, a linear alternator or a rotating armature with a stationary magnetic field is used. In principle, any AC electrical generator can be called an alternator, but usually the term refers to small rotating machines driven by automotive and other internal combustion engines. The alternator uses a permanent magnet for its magnetic field is called a magneto. Alternators in power stations driven by steam turbines are called turbo alternators. Large 50 or 60 Hz 3-phase alternators in power plants generate most of the world's electric power, which is distributed by the electric power grids. In an alternator, the magnetic field rotates and the variable 3-phase AC which is generated by the stationary stator coils, is converted into 12 volt DC by an internal rectifier circuit. Automotive alternators have the distinct advantage that they are specifically designed to charge 12 or 24 volt batteries. Although a good 5 or 7 foot diameter 3-bladed rotor which will reach the speeds in excess of 1000 rpm, this is still too slow to be a good match for most common car alternators that rotate at speeds of between 2000 and 10,000 rpm as they are attached to the car's engine. So a gearbox or a pulley system would be required to increase the speed at which the alternator spins and to increase the output of the alternator. Also, the automotive alternators require an additional external power supply to provide a small biasing current. The dashboard indicator lamp usually used to their field coils to start the excitation and therefore the generation process before the alternator reaches in cut-in. This external field current could be supplied by the attached battery bank, but the problem with this is that the batteries would continue to supply the current, possibly draining the batteries even when the turbine blades are stationary during the periods of zero or the little wind. Another problem with the modern automotive alternators is that they are built up for the cheapness and the lightweight, so usually only have the small 5 to 8 inch or the 17 millimeter diameter rotor shafts to mount a pulley on which may be a little on the small side to take the weight and stresses of the rotor. Now come to the references. From these references I make the tutorial. You can go through these references. Thank you.